Welcome back everyone to GenChem Lab. Today is Wednesday, April 15th, and unfortunately it's snowing outside and it's really cold, but I decided to distract myself by talking to you about some exciting acid-base chemistry. So in this video we'll cover pH of salts and pH of buffers. We're going to also look briefly at what's called Bronsted theory. So just a quick reminder, I'm sure this should be familiar from lecture. Acid in Bronsted theory is considered a proton donor, while a base is considered proton acceptor. Why is that relevant and why is it so important? Well, sometimes students have difficulty writing equations for acid-base reactions, but that task can be significantly simplified by simply remembering that any acid-base reaction can be considered proton transfer from acid to base. So when looking at potential reactants, all you have to do is figure out which way proton will travel. And as an example, I'd like to consider an equation of a reaction between a strong acid such as sulfuric acid and water. I picked sulfuric acid because we don't talk about it too often, but it's a very commonly used strong acid. So let's consider what happens when we put sulfuric acid in water. Here, obviously, this being strong acid is going to be our Bronsted acid, and water in this case is going to act as a Bronsted base. It may be weird to think of water as a base, but in this instance it is. Another thing to keep in mind about water is that water can be either acid or base depending on what is placed in it. And so in this case, water acts as a base, proton is transferred from sulfuric acid to water. So question is, what are the products going to be? Well, think about it. If we take H plus away from H2SO4, what's going to be left is HSO4 minus, or hydrosulfate ion. And this is going to be a conjugate base of sulfuric acid. So we remove the proton from acid, and we got a conjugate base of that acid, in this case, HSO4 minus. And then when we added the proton to water, we of course generated hydronium ion. And this is why the solution of sulfuric acid and water will have quite a bit of hydronium ion in it. Notice that arrow is pointing only one way from reactants to products, indicating that sulfuric acid is a strong acid and this reaction is going to occur to completion. So having reminded you about Bronsted acids and bases, we're now going to concentrate on salts. And when considering pH of salts, one thing to keep in mind is that aqueous solution of salts are often thought of neutral solutions, which of course is not necessarily the case. Some salts are neutral, but there are plenty of acidic and basic salts as well. So how would we differentiate between those salts? Well, one thing that I would like to call your attention to is that in the lab manual, on page 139, there is a table 2 on the bottom of the page, that basically looks at 4 types of salts and how you can determine whether a particular salt will be acidic, basic, or neutral. And basically the idea is quite simple in here. You basically are looking at what kind of acid and base produce the salt. For example, if a salt is formed by a strong acid and a strong base, such salt is expected to be neutral. If a salt is formed by a weak acid and a strong base sort of wins over and the salt is going to be basic. And finally, if a salt is formed by a strong acid and a weak base, then such salt will be considered acidic. So I'd like to change things up a little bit, and I would like to show you some things first and then we can discuss. So what I have over here is an array of various salt solutions. And if you look at data sheet 2 on page 150, you will see there is a listing of various salts. I may not have them in the right order here. Let's see, I'm missing sodium chloride because it's over here because I was going to start with it. So first salt on our list is 0.1 molar sodium chloride. So what I have over here is Pasco data logger which is right now acting as a pH sense or pH meter. I've included a video on Canvas for you from Pasco that shows how pH meter can be calibrated and used for measuring pH. I've already showed this to you, so hopefully this is familiar as well. This is a pH electrode, which right now is sitting in tap water, and you can see that tap water is slightly basic. It's about 7.7 in pH units. I'd like you to think about sort of a side question as to why tap water happens to be a little basic. Hint, it has to do with salts that are dissolved in it. But for now, what I'm going to do is I'm going to take out my electrode. I'm going to rinse it in some dry water, make sure membrane is clean. And here's my first salt, which is sodium chloride. And I'm gonna put the electrode in here. I'm gonna have to hold the beaker so I don't have a disaster of it spilling. It's not doing what I want it to do. Maybe it is. I just have to wait a little bit. Okay, let me check something real quick. Okay, we're gonna stop the video for now because I need to recalibrate the pH meter. Sorry everyone.